All right, guys, I'm creating this video to really help you understand transformation of functions a little bit better. So we're looking here at the function h of x equals x squared, and then I've written another function that you don't see right now, where there are four parameters: a, b, c, and d. And parameter a I've currently set to equal 1, and b I've set to equal 1, which means we're multiplying by 1 and there's no real consequence. And c has been set to about 0, so that we're not adding or subtracting anything either. And right now d is set to 0. So all we see is the function h of x equals x squared. But let's look just at d. If I start moving point d, and I make d approximately 2. It's hard to get exact with this program, but you'll get the idea. If I make d approximately 2, what happened to my graph? My y-coordinate shifted exactly 2 places up, so that adding this number here outside of the function affects the vertical shift and shifts my graph up or down by the amount that I have added. So that if I add a negative number, -3, my graph has moved down 3. So this d parameter here affects the vertical shift. I can move my graph up or down by adding a number outside of the function. Now let me sort of reset that to approximately 0 so we can focus on a different parameter. Oh, I had it at 0. There it goes. All right, let's look at parameter c. Parameter c is inside the function. And we are, again, looking at adding or subtracting numbers. So right now it's set at c. Let's maybe make c equal to 1. All right, so when c is approximately 1, what happened to our graph? Our graph moved 1 place to the right. When c is approximately 2, our entire graph, and it's really easy to see it by focusing on the vertex, but our entire graph moved 2 places to the right. If c is a negative number, for example, c is -1, our graph moves 1 place to the left. So adding or subtracting outside the function shifts the graph up or down, and the graph seems to behave the way we would expect. When you add a number, the graph rises. When you subtract a number, the graph falls. When you add a number inside the function, it's again a shift, but it seems to behave somewhat backwards. When you add a number, when you subtract 2, your graph moves 2 to the right. When you add 2 by subtracting -2, your graph moves 2 to the left. So here we're going to subtract -2, and our graph moves 2 to the left. But adding or subtracting numbers still always is a translation, a shift that occurs in our graph. Now let's take a look at what happens. I'm going to put c back to 0 because it's confusing when there's too many transformations going on at once. So now let's take a look at what happens with a. A is a transformation, a multiplication that happens outside of the function. Because it's a multiplication, it ends up, let's see what happens. Right now a is 1. What happens if we make a 2? Okay. All right. Right now, I know that a lot of you were going to think, oh, the graph shrunk, it narrowed. And that's a very logical thing to think of when you look at a transformation with a parabola. In a minute, I'm going to change which function we look at because it's easier to see what's going on that way. But I want you to see that we could think of this as narrowing, but the way we need to think of this transformation outside the function is that it's rising more quickly. So that before, when we had x is 1, we had y is 1. But now, when we have x is 1, we have y is 2. Before, when we had x is 2, we had y was 4. Now we have x is 2, y is 4 times 2, or 8. So the graph is actually rising more quickly. It's a transformation in the vertical axis, and it's stretching it. it's much easier to see this transformation if we change our function, and instead of using the x squared function, we use the function sine of x. And I need to go and edit my preferences really quickly so that I have my angle in radians. Otherwise, I'm not going to get a display that you can understand. Okay, so now our original function, again, the blue function. And let me make this axis a little bit, spread it out so we can see the function better. Okay, here's our original function. It took from 0 to a little more than 3 for our graph to go up and to go down. And, oh, whoops, forget that. Our graph had a maximum point of 1, and now it has a maximum point of 2. If I continue to manipulate point C, point A, and I make it 4, now our graph has a maximum of 1. Before, our original graph had a maximum of 1, now it has a maximum of 4. If I make a fractional value less than 1, my original function had a maximum point of 1, now it has a maximum point of 1/2. So multiplying outside of the function affects the vertical stretch or shrink, and it behaves exactly as we would expect it to behave. If we multiply by a number that's larger than 1, our graph has a larger stretch than 1. If we multiply it by a number that's less than 1, our graph has a stretch that is less than 1, and our graph is not as high, not as tall. I'm going to reset this to approximately 1 so we can look at the harder one. The hardest one to look at here is B. Let's take a look at what happens with B. I think you could probably figure, since B is happening inside the function, that we would expect this to affect our graph horizontally. And maybe you might even expect that because it's inside the function, it operates almost backwards from what we would expect. So let's just take a look and see what happens. I've made B about 2. Now, let's take a look at what happens. When B is 2, this did affect the horizontal shift. But how? Our original graph took from 0 to a little more than 3 to go up and to go back down to get to this point here. In our new graph, how long did it take? It took from 0 to a little more than 1.5. So although I multiplied by 2, in fact, to get from this spot to this spot on my transformed function took half the amount of time that it took before, or half the amount of distance, so that this point here on the blue graph really moved to here. If I look at the original blue graph, it took a little over 6 to get to go up and to go back down. On the transformed function, it took a little more than 3. It took half the amount of space. If I made B3 approximately 3, on my original graph, again, it took about 6 for me to get, a little over 6 for me to go up and back down. And on my transformed graph, it took me a little more than 2, and 6 divided by 3 is 2. So how do I get my transformed graph to be wider? Well, if I multiply by a number that's more than 1, it seems to sort of make it more compressed. So what happens if I multiply by a number that's less than 1? Maybe 0.5. This is about as close to 0.5 as I can get. When I multiply by 0.5, my original function, again, the blue function, took a little more than 6 to get, well, I can't even actually see it all in my stretch graph. So let's say it took a little more than 3 to go up and down. And on my stretched graph, it took a little more than 6. By making B 1/2, my graph actually stretched by a factor of 2, by the factor that was in the denominator. If I made b around 1/3, so around 0.33 somewhere, my original graph took me a little more than 3 to go up and down, and my new graph is going to take, sort of look at this, it takes a little more than 9, 3 times 3 to go up and down. So the effect of B is to affect the horizontal shift, and it works sort of backwards because it's inside the function. That's enough on individual transformations. I'm going to make one more video, which I will also post, which will look at combined transformations.